Lesson 11.4, Lines and Planes in Space. Let's talk about three-dimensional lines. Not as simple as just y equals mx plus b. If you expand that with a z, you have like ax plus by plus cz equals something. That is actually a plane, not a line. So imagine this. Line L goes through points P and Q. So you can see in the picture, Q is x, y, z, P is x1, y1, z1. V is a direction vector for L, so it's going the same direction as L. So we can call that ABC. If we start at P and move any distance in the direction V to get some point Q. So we're starting at P and we're going some direction in the direction as V. They're parallel to each other. We end up at Q. Therefore, vector PQ is the same as T times vector V because they are parallel, so they're a multiple of each other. So, to find vector PQ, it's just Q, xyz, minus the point P, x1, y1, z1. And then the TV, we just distribute the T through the A, B, and C. This is known as the general form. We can take that general form and change it into what's called the parametric equations of a line. Just take each component, the x component, the y component, and the z component, and then solve them for x, y, and z, and you end up with that. This is what we used when we did 3D systems of equations that got many solutions. Remember, we're going to say, oh, let z equal a, and in this case, we'll let z equal t, and it works out. Or we can solve them all for t and get the symmetric equations of a line where they're all equal to each other because they're all equal to t. The most common one used is the parametric equations of a line. So let's find a set of parametric equations of a line that pass through those 2 points. So first, we need a direction vector. So that would be our vector v, and just subtract the 2 points. So we'll have 4 minus 1, 0 minus 3, 1 minus negative 2. So v is 3, negative 3, 3. That is our A, our B, and our C. Now, we have enough stuff. Plug into the formula. So as x equals at plus x1, y equals bt plus y1, and z equals ct plus z1. So a was 3, t, and we just need to pick one of the points. Let's pick the first one as x1, y1, z1. It doesn't matter. If you use the second point, you'll also get the equation of the line. It'll just look different. If you pick different values of t, then you get the other one. B is negative 3, and y1 is 3, c is 3, and z1 is negative 2. So that is our answer. If you were to plug in different numbers at t, such as 0, you get 1, 3, negative 2. If you plugged in a 1, you'd get 4, 0, 1. Oh, that's our other point. So it seems to work. If we had used our other point, you could plug in values for t and get the first point. So what this is, this just gives you all the points on the line. Planes. Planes are like three-dimensional lines. They're infinitely long in 2 dimensions, but infinitely thin in the 3rd dimension. If we look at our picture here, it says PQ dot N equals 0 because they are perpendicular. Well, where's P and Q? All right, well, let's take a point here and call it P. And a point over here, and we'll call it Q. So we have a vector PQ. Point P can be x1, y1, z1. Point Q can be x, y, z. All right, they're perpendicular. N is called the normal vector to the plane because it's perpendicular. In math, the word normal means perpendicular. And so if we dot product those, we end up with standard form, where it's the x times the x. So remember, PQ is going to be the difference in the x's, difference in the y's, difference in the z's. So if I dot product, it's multiply the x's plus multiply the y's plus multiply the z's, and it equals 0. If we knew the numbers for x1, y1, z1, we could multiply it out and get the general form, which is that. Let's find the general form of the equation of a plane passing through those 3 points. First of all, we need to find the normal vector N. All right, how we're going to do this is start by find 2 vectors in the plane. And so what I'm going to do is I'm going to find vector AB, which would be 1 minus 3, 5 minus 2, 0 minus 2, or negative 2, 3, negative 2. And I'm also going to find vector BC, which would be 1 minus 1, negative 3 minus 5, and 1 minus 0, or 0, negative 8, 1. Then we cross product, because the cross product result is perpendicular to the 2 vectors. So our N is going to be equal to AB cross product with BC. So we have the I, J, K, negative 2, 3, negative 2, 0, negative 8, 1. Copy the first 2 columns. Looks like I have 3I, 0J, and 16K minus 0K minus 16I minus a negative 2J. So it looks like we have negative 13 I's, 2 J's, and 16 K's, or negative 13 to 16. That is our A, our B, and our C. All right. So now we fill in the standard form, which is ax minus x1 plus b times y minus y1 plus c times z minus z1 equals 0. But I need to pick a point. Any of the points on the plane will work. So I'm just going to pick point B, 1, 5, 0. So A, so I'm over here, negative 13, x minus x1, which is 1 from our point B. Little b is 2 minus 5, x1, y1, z1. And C is 16, z minus 0. All right, now we just have to simplify to our general form. So we'd have just distribute, so it'd be negative 13x plus 13, 2y minus 10, 16z equals 0. So it looks like I have negative 13x plus 2y plus 16z plus 3 equals 0. We can find the angle between two planes because using geometry we can show that the normal vectors, the angle between the normal vectors is the same as the angle between the planes. If you remember to find the angle between two vectors, it's the dot product equals the magnitude times cosine of the angle. We can also find the distance between a point and the plane. If we have point P, which is what we're looking for the distance from, and point Q, which is on our plane, we just need to find the projection of that onto the normal vector, and the magnitude of that will be the distance. So if you remember, the projection is simply, or the magnitude of the projection will simply be the dot product of PQ with n divided by the magnitude of n. Now let's go over graphing planes in space. First thing to do is to find the intercepts. Then you plot the intercepts. And then you draw a triangle to represent the plane. So what you're going to do is you're actually going to draw the plane that's in one octant. And just remember it extends in all directions. So let's sketch that. All right, so first of all, we need to find the x-intercepts, or all the intercepts. Find the x-intercept. You let the other variables be 0. And we'll get x is 8. And I can put that on my graph. Then find the y-intercept. The y is y, everything else is 0. I think you get y is 6. Put that on the graph, on the axis. And then the z-intercept. The x and y are 0s, and the z is not. And looks like you get z is 4. So put that point there. Then we're going to connect these with lines. And so that is the plane that goes through the first octant, and often it's kind of shaded. And remember, that just represents the slanted plane. It really truly extends in all directions.